I'm Jiacheng from the Chinese University of Hong Kong. I'm here to introduce our paper, Ditto, an elastic and adaptive memory-disaggregated caching system. The name Ditto is a Pokemon that can arbitrarily change its appearance, and this is a joint work from CUHK, Fudan University, Yangfan University, and Huawei Cloud. In-memory caching systems are fundamental building blocks for many cloud applications like databases, online gaming, and serverless platforms. The elasticity is a critical requirement for all these applications since they all exhibit bursty workloads and require these caching systems to quickly adjust compute and memory resources during workload change. Existing in-memory caching systems are constructed with and deployed on monolithic servers. Clients send RPCs to the caching server and rely on the server CPU to access and modify cached objects. There are two issues when we want to add more CPU or memory resources under this architecture, and the first is the inevitable resource waste. Existing approaches allocate resources in the granularity of fixed-sized virtual machines with both CPU and memory. So this wastes CPU when we only want to add more memory to increase the cache size, or wastes memory when we only want to add more CPU cores to improve the overall throughput. And the second issue is the slow resource adjustment. Existing caching systems on monolithic servers adopt a shared nothing architecture. They partition data on multiple machines and route client requests according to the shard of data. And under this architecture, data have to be migrated and resharded every time new resources are added into this cluster. And such data migration is unavoidable when either we want to add more CPU cores or more memory due to the coupled allocation of CPU and memory on monolithic servers. Besides, clients have to wait for minutes when migrating data, and the performance of the entire system will be negatively affected. To show the effect of data migration on resource scaling, we'll conduct experiments on Redis, one of the most widely used caching systems. And we first create a 32-node Redis cluster, scale it out to 64 nodes, and then scale it back into 32 nodes. And Redis takes up to 5.3 minutes to migrate 10,256 byte KV pairs, and the overall throughput drops up to 7%, and end-to-end latency increases up to 21%. To address these elasticity issues, we propose to port in-memory caching systems to the disaggregated memory architecture to provide better elasticity. DM decouples the CPU and memory into independent compute and memory pools and connect the two pools with fast CPU bypass networking techniques like RDMA and CXL. The compute pool contains many CPU cores and a limited amount of local DRAM to serve as the runtime cache. And the memory pool holds abundant memory, but a limited number of CPU cores to serve management tasks like network connection and memory management. On DM, resource waste can be mitigated because the CPU and memory can now be allocated separately in a finer granularity. And moreover, the resources can be scaled rapidly since the compute nodes can now access all data in the memory pool. This eliminates data migration from the critical path of resource scaling. However, two challenges have to be addressed to achieve a practical caching system on DM, and the first is how to execute caching algorithms. Executing caching algorithms requires monitoring object accesses and maintaining object hotness in caching data structures. For caching systems on monolithic servers, clients use RPCs to access data. So this makes the CPUs of the caching server a natural centralized data access monitor since all requests are processed by these CPUs. Moreover, the caching data structures can be efficiently maintained in the local DRAM of these caching servers on each data access, since data access changes object hotness. However, for caching systems on disaggregated memory, clients directly access and modify cached objects and caching data structures with one-sided RDMA verbs. In this situation, the memory pool cannot monitor data accesses since they are bypassed by RDMA when clients access data. And meanwhile, individual clients also cannot monitor data accesses since they are only aware of local access information, while executing caching algorithms requires global access information to measure the hotness of cached objects. Moreover, maintaining these caching data structures becomes inefficient on DM due to the multiple microsecond scale remote memory accesses and expensive remote synchronization when clients need to concurrently access these data structures. And consequently, executing caching algorithms on DM is hard due to the difficulty in monitoring object accesses and maintaining caching data structures. And the second challenge is that the changing compute and memory resources on DM can affect the cache hit rates of different caching algorithms. This makes cache systems on DM hard to achieve high cache hit rates. First, the change of compute resources can affect the cache hit rate. This is because on DM, applications execute multiple client threads in the compute pool, and different applications can have different data access patterns. The overall data access pattern is the mixture of all clients in the compute pool. And the change of compute resources can alter the number of clients under a particular data access pattern and alters the overall data access pattern. And the change of memory resources can also affect the cache hit rates, since the hit rates of different caching algorithms change differently when we increase or decrease the cache size. For example, under a particular data access pattern, LRU may perform better under a small cache size, but when we increase the cache size, LFU can become better since it is more sensitive to the increase of cache size than LRU. According to our simulation results on the real-world webmail workload, the better caching algorithm among LRU and LFU changes as we alter the compute and memory resources, and thus it is difficult for caching systems on DM to stably provide a high cache hit rate under changing compute and memory resources. To summarize, two challenges have to be addressed to construct a practical caching system on DM, which are efficiently executing caching algorithms and stably providing high cache hit rates. We propose Ditto to address this challenge. Ditto is composed with clients in the compute pool and objects in the memory pool. And applications use Ditto clients to access and modify cached objects, and we use a hash table to organize the objects in the memory pool. We propose a client-centric caching framework to efficiently execute multiple caching algorithms and proposes multiple eviction candidates during eviction. And various caching algorithms can be integrated into the framework with little coding effort. A distributed adaptive caching scheme is then proposed to use machine learning to learn the characteristics of the current data access pattern and select the final eviction victim according to the performance of executed caching algorithms. So the major challenge the client-centric caching framework addresses is how to efficiently monitor data accesses and maintain caching data structures. Our idea is to use distributed access monitoring with sample-based eviction to address these two challenges accordingly. First, the distributed access monitoring associates each object with a small metadata indicating their access information, for example, timestamp and frequency counters. After each get and set operation, clients use one-sided RDMA verbs to update this metadata asynchronously. And during eviction, we sample multiple metadata from the memory pool, and on the client side, we use a priority function to map this metadata to real values indicating the hotness of this object in the cache. And the overhead of the maintaining caching data structures is eliminated. And since the key difference among caching algorithms is their definition on the hotness of cached objects, various caching algorithms can be integrated by defining their own priority functions. However, achieving such a framework on DM requires many additional RDMA requests to update this metadata and to sample objects. We propose a sample-friendly hash table and a frequency counter cache to address this issue. The sample-friendly hash table stores the metadata of objects in the slots of the hash table instead of together with objects. So we summarize the most commonly used access information and maintain them by default in the hash table. And for each cached object, we maintain an insert timestamp, a last access timestamp, and a frequency counter. And the last access timestamp and frequency counter is updated with an RDMA write and an RDMA fetch and add after each data access. And with this sample-friendly hash table, sampling can be efficiently achieved with only one RDMA read by reading continuous slots from the random offset. And then the frequency counter cache batches the updates to the frequency counter to reduce the number of RDMA fetch and adds. And we cache the value, update the value of frequency counter locally on clients and update it together to the memory pool when the cached value exceeds a threshold. And by setting the threshold to t, the frequency counter cache can reduce the number of RDMA fetch and adds by up to t times. And then the distributed adaptive caching scheme adapts to the changing resources and workloads on DM. And the key idea is to formulate the cache replacement as a multi-armed bandit problem and use regret minimization to adapt to the workload changes. Specifically, we rely on the client-centric caching framework to execute multiple caching algorithms and proposes multiple eviction candidates as experts in MAB, and we associate each expert with a weight indicating their performance on the current workload. In the memory pool, we maintain a fixed-size FIFO eviction history to perceive the performance of these executed experts. And during eviction, we first apply multiple priority functions on the sampled objects and select the final eviction victim according to the weights of the experts. And the key of the evicted object and the expert chosen to evict this object is appended to the eviction history after each eviction. And during normal data accesses, there will be a situation when we find a key missed in the cache, but we find it hid in the eviction history. Then we should reduce the weight of the expert chosen to evict this victim because it has made a mistake. However, two problems need to be addressed to achieve such a pipeline on DM. And first, maintaining this FIFO eviction history is expensive on DM due to we need to maintain an additional index to index these history entries, and we need to maintain an additional FIFO data structure. And besides, updating and accessing these expert weights as additional synchronization overhead among clients in the memory pool. So to address the first problem, we propose a lightweight eviction history with in-cache history entries and a logical FIFO queue. The in-cache history entries reuses the slots of the hash table to store the history entries. And on each eviction, we use an RDMA companion swap to atomically modify the size and the pointer field of the original slot to mark this slot as a history entry and to record a history ID. And we record a bitmap indicating which expert chose to evict this victim into the insert timestamp field asynchronously. And the history entries are later evicted and converted into normal slots when it is considered expired in the FIFO queue. Such a design enables history entries to be normally indexed with the same hash table as the cached object, and the memory space for storing these history entries can also be saved. Then the logical FIFO queue judges if a history entry is expired or not without maintaining the actual FIFO data structure. We maintain a global history counter in the memory pool and generate history IDs for history entries by atomically increasing this global counter. And then we can view these history IDs and global counter as locations in a logical buffer. And by viewing the global history counter as the tail of the queue, we can construct a logical FIFO queue. And we can easily judge if a history entry is expired or not by comparing its history ID with the length of the queue. And we defer the eviction of expired history entries when new objects are inserted. And by then, we directly view the expired history entries as empty slots and modify it to point to the new object. Finally, to reduce the overhead of synchronizing expert weights, we propose a lazy weight update scheme. We cache the copy of global weight on clients locally and buffers the penalties to the global weight. And periodically, we send the copies to the controller of the memory pool and rely on the controller to update and synchronize expert weights. And more design details can be found in our paper. We evaluate Ditto with both YSSB hybrid workload and real-world key value traces. And we use the Clemson cluster of Cloud Lab to conduct all our experiments. And we use 8 machines to construct our compute pool and 1 machine to simulate our memory pool. We set Ditto to adaptively select among LRU and LFU. We compare it with ClickMap and Redis to state-of-the-art in-memory caching system. And we also compare it with Ditto LRU and Ditto LFU to baseline approach that only use LRU or LFU as its caching algorithm. And this figure shows the elasticity of Ditto compared with Redis. And compared with Redis, Ditto can separately scale CPU and memory resources. And the performance gain and the resource reclamation happens instantly since we do not involve any data migration in the resource scaling process. And this figure shows the efficiency of Ditto of executing caching algorithms on the write-intensive YSSB-A workload and the read-only YSSB-C workload. And Ditto reaches up to 9 times higher throughput compared with ClickMap on disaggregated memory. And finally, we show the adaptivity of Ditto under changing compute and memory resources. As we can show in these figures, the hit rate of Ditto can approach the better one of LRU and LFU and can exceed both under changing workloads. In conclusion, existing in-memory caching systems suffer from the poor elasticity and the limited resource utilization due to their adoption of monolithic servers. And in this paper, we propose Ditto, The first memory-disaggregated caching system with a client-centric caching framework and a distributed adaptive caching scheme to provide higher elasticity. And our experiments show that Ditto outperforms the state-of-the-art approach by up to 3.6 times in real-world workloads and 9 times in YSSB workloads. And Senko and Ditto is open source. You can access Ditto through this link, and I'm ready to take any questions.
You can start.
Yeah, thank you. Hanze Zhang from Shanghai Jiacheng University, and I have a brainstorm-like question. So, as you have mentioned before, disaggregated memory can be linked not only by RDMA networks, but also by CXL-based. Yeah, so I wonder, do the challenges you have mentioned in this work still hold in the CXL-based network? And can your techniques and principles still be working, or does there any extra application under this scenario?
Thank you for your question. Yeah, actually, I believe the CXL and RDMA have the same assumption in this work, which is we bypass the CPU in the memory pool. And so they have the same problem as we do in RDMA. And the only assumption we made in our RDMA is that it can read the remote objects, right, and it can perform some atomic operations like compare and swap and fetch and add. So I believe CXL can easily be integrated into this.
Okay, and thank you. And do you think there is more opportunity for leveraging the cache coherence mechanisms of CXL to, even putting part of the cache onto the compute nodes to get a higher, even higher performance?
Right, I believe that will be a great design choice. We can surely store some data on the compute pool if we have some memory consistency and cache coherency, right?
Yeah, very good talk. Thank you.
Thank you.
Yeah.
Hi, Stuart Grant, UCSD. Excellent work. I know that the rate limit on fetch and adds is about 1 million operations per second. Did you find that that actually caused any sort of issues on the real-world workloads, updating the frequencies?
Yeah, according to our results in our paper, they actually we use fetch and add in our distributed adaptive caching scheme, right? So in our experiments, we find that the overhead of using this additional fetch and add is about 5% compared with pure LRU and LFU.
Okay, thank you.
Thank you.
Hi, Shaurya Patel, UBC. This is really cool work. I'm a bit intrigued by your latency results because I wanted to know, like, when you compare to Redis or something else, what kind of caching algorithm is applied to that system? Because I would imagine that while you are in the learning phase with your adaptive caching policy, like it might select a bad caching policy. So I thought that we would see high latency during that period until it learns the policy. So I wanted to, I was curious about this. Like, did you see such a behavior?
Sorry, I do not quite follow your questions.
So in your latency results, like Ditto always performs very well. But when I thought that when you are using adaptive caching algorithm, it might have some bad predictions in the beginning when it uses a bad algorithm. So have you noticed such a behavior that due to this, there is some latency spikes?
Oh, right. These two figures actually shows the performance of Ditto of executing caching algorithms. So we do not have cache miss on these experiments. Right.
But is the adaptive algorithm active during this time? Or have you already selected, like, has the learning agent already learned the algorithm for this particular graph?
No, actually the adaptive works in this experiment. And since the adaptive works only on cache miss, and it's the only time we need to adjust the weights of experts and right. So this experiment do not involve any cache miss.
Oh, I see.
It just shows the efficiency of executing different caching algorithms.
Okay, thank you.
Hi, Anil Yalam, UCSD. Really nice work. So my question is about the result that you showed on slide 13, I think. So where you showed the LRU versus LFU outperforming each other at different memory settings. And so I kind of wanted to ask can you speak a little bit to the intuition behind why that's happening, especially like when you change, all you change is just the memory, cache memory.
Oh, you are asking why ARRU is
Yeah,
performing
just like
better in a
yeah.
smaller cache size?
Yes.
Actually, this is because the ARRU and ARRU select reserve different objects in the cache size when they execute, and the difference is maybe so their decision results in the difference when we change the cache size. They reserve different objects, right?
Okay. Okay. Well, thank you. I'll follow up offline. Yeah, thanks.
Let's thank our speaker again.